Okay, so then let me carry on. So the lecture notes that I posted in last time, I wasn't able to cover all of that. So let me just go back. So so today we will see a more rigorous derivation of the fact that what we assumed last time. Last time, what we assumed was that the energy that maximizes this combination E is E total, with respect to S1, E1, the solution to this guy, which maximized the argument in the exponent of this thing. So this also maximized, the entropy. Well, yeah, that's exactly what we're doing. So this is e to the power this thing. So this thing is over here. So we said that was going to be the physically realized state of the system. That solution, to that equation, we call that E star. So this means that we are identifying what is the physical with what is the most probable, or what is the average, right? So today I'm going to give an argument of this in the limit in which the number of systems go to infinity. So in the limit where the number of particles go to infinity, and this is known as the thermodynamic limit, okay? So that's coming up. So because the argument I gave you so far was more heuristic, but before we do that, let me introduce the concept of temperature. So microscopically, how do we define temperature? We define the temperature by saying that if T is temperature, then 1 over T is the derivative of S with respect to energy. I'm using partial derivatives here, but if S is so far we have only assumed S to be a function of energy. In that case, this is also just a total derivative, right? In case of a function of one variable, partial derivative and total derivative are the same thing. Okay. So it should be obvious that T at least has the right dimensions, right? T has the dimension of temperature. And that's because K. Boltzmann had the dimension of joule per Kelvin. That was the units, not the dimensions. Okay, so T has the right dimension. Now let's see that T has the right properties, okay? Now, what we've established there above is that in equilibrium, when we bring two systems together in equilibrium, we get that the entropy of the two systems must agree, right? That's basically what we showed above, right? This is just this, this equation. Of course, what we're using here is the fact that delta d by dE1 is equal to minus d by dE2, right? So thus we see that when they are at equilibrium, the temperature of the two systems must be the same, right? And let's call that T. So at least we have established one important property of the temperature that our definition satisfies. Sorry. So let's look at two systems which are slightly out of equilibrium. Okay. So this was at equilibrium. And then we take two systems which are slightly out of equilibrium and we bring them together. And in that case, the change in entropy so we get delta S is going to be delta S1, which is a function of E, and then delta of E, and we can write this as delta of E1, and then we have delta S2, and this is a function of E2, and this is going to be delta of E2. And the notation here is saying that we take the derivative with respect to its argument with respect to E and set it equals to E1. So now what we do is that the first thing becomes 1 over T1 delta of E1, and the second one becomes 1 over T2, and this becomes delta of E2. Okay. Now, just 1 second. Yeah. Now, if I look at conservation of energy, then the conservation of energy tells me that if I change delta of E1, then that should be equal to delta of minus E2. And this is something that we assume because we are dealing with the microcanonical ensemble and we are keeping the energy fixed. So if I do this, then my delta of S becomes 1 over T1 minus 1 over T2 times delta of E1. So previously, from the second law, we established that delta of S should be greater or equal to 0. So this means that if, say, T1 is greater than T2, that the first object is hotter than the second, second object, then of course this is negative, right? But this is negative, but this is positive. Therefore, delta E1 has to be negative. Okay. So what does that mean? That means that the energy in case of two systems, say 1 and 2, where T1 is slightly bigger than T2, and we bring them together, the energy will flow from the hot object to the cold object, right? Because that means that the first object is losing energy, right? So we see that the temperature as, defined by 1 over T equal to delta S by delta E has all the right properties, okay? So this is the definition that we adopt for statistical mechanics. Okay, any questions?
No, I don't think so.
Okay.